So hey guys, welcome back to the channel, and if you are new to the channel, welcome. In this video we are going to start the architecture of 8086. We are going to discuss all the things which are there in this architecture. So the basic thing about 8086 is that it is a 16-bit processor. That means whatever the operations are going on, it does with the 16-bit, and it transfers the 16-bit data at a time. So here it has this ALU of 16 bits, and let's see the architecture. It is divided into two sections, that is BIU and EU. So BIU stands for bus interface unit and EU stands for execution unit. So now you might ask, why is it divided into two sections? Then the answer is pipelining. Pipelining is the process when you execute some instructions over here. At the same time, this microprocessor fetches another instructions from the memory at the same time, and it gets stored in the prefetched queue. So here the advantage of using this 8086 microprocessor is it saves time. So whenever the instructions are getting executed, at the same time another instructions are getting fetched from the memory. That means we are not going to wait till the completion of this execution. We are fetching already the instructions from the memory, and that is stored in a prefetched queue. So whenever this instruction will get executed, another instruction will get into the pipeline, and after that it will get executed in the ALU. And so in the whole diagram you can see more rectangle boxes, but these two diagrams are a little bit different. So what are these two diagrams? These two blocks represent arithmetic operations. It means these two blocks are going to do arithmetic operations like addition, subtraction and all those things. So basically it is like, if we give two operands here, it will perform some operation over here and it will give some output. So it's like this. So whatever arithmetic operations are there, that is performed by this block. Note one thing here, that both of these are not ALU, that is both of these are not arithmetic logic unit. Both of these are not going to perform the same task that the ALU is going to do. This ALU will perform the arithmetic tasks only, but this will calculate the physical address of the instruction in the memory, and we get the physical address by applying this formula, that is physical address is equals to the segment into 10 plus offset. Let's discuss why are we getting this formula here. Now let's discuss memory segmentation. So here the memory is divided into four segments, that is code segment, stack segment, data segment and the extra segment. The code segment will contain the code, stack segment will contain the stacks, and the extra and the data segment will have some extra code in it. And here the 8086 has a 20-bit of address bus. So 2 to the power 20 is equals to 1 MB. Now the memory is of 1 MB. Let's consider you have a hard disk of 1 terabyte. So it will have 1 trillion locations in it. Now if you want to store something in the memory, or you want to retrieve something from the memory, do you want the address, that is the real address in the memory? No, right? You will just make a folder in your system and you will just make another file in that folder. So the folder and the file is the location that you want the information from, but is it the real address of that folder and file? No, right? The real address is something else. The folder name and the file name is given by you, so that is not the real address. But is it necessary for us to get that real address? No, right? We don't care about it, but the processors do care about it. They want the physical address to retrieve that data and show it to you. So it has 1 trillion locations and addresses, but as a programmer we don't want that headache. We want simplicity. So this ROM memory of 1 byte is divided into 4 sections: code segment, stack segment, data segment and extra segment. As let's consider you take a notebook or a textbook. In textbook we have our 5 chapters, and in 5 chapters you want to address to the third unit, and in third unit you want to go to the 16 page number. So you will say that go to 16 page of third unit. So third unit is one stack here, and 16 page is the offset addresses in those stacks. So here CS, SS, DS and ES are the segment addresses or segment addresses, and the remaining, that is IP, SP and BP, SI and DI are the offset addresses. So as I told you the formula on the previous page, that physical address is equal to this segment into 10 plus offset address, right? So let's consider this segment address as 1000 and this offset address as 2345. That means this 1000 is the segment address and this offset address is IP. So now if I add it, we will get this. So this is the physical address of the instruction that is in the memory. So do we need this address? No, right? The processor needs it to fetch the data from the memory and to perform the operations whatever are given in the program and then display the output. So now let's get back to the block diagram. Here, what is this BIU doing? BIU is fetching the instruction from the memory and it is calculating the physical address. Also, it is doing one more thing, that is, it is sending this instruction to the 6-byte prefetched queue. So we have understood what this ALU is doing, and let's understand what these are. So these you saw in the segmentation explanation. These are not segments, these are segment registers which store the address of all those segments which I showed you in the previous page. That is, the address of all the segments are stored in the segment registers, which is over here. Now it tells the starting address of all the segments. So this IP, it contains the offset address, and CS, it contains the segment address. So both of this work together and performs the operation, and it calculates the physical address. So as the instructions are fetched, are we going to execute it? No, right? Because already some another instructions are getting executed. These are pre-fetched data which will get stored in this 6-byte of pre-fetched queue, and after that it will get into the ALU after completion of the first instruction that was getting executed. So this will fetch the instruction from the memory, will put it into the 6-byte prefetched queue, and after the completion of the instruction that was going on, it will one by one get executed in the ALU. After completion of one, the next instruction will get into the ALU and it will get executed. And then after completion of that one, another instruction will come into ALU and that will get executed. Now you might think that if this first one is getting into the ALU, then the last one will get empty, and then only 5 instructions will be there in the prefetched queue. So will it get refilled after the 1 byte is getting empty? No. It will get refilled only when 2 bytes get empty. That means 1 will get executed, then 2 will also get executed. So after that, we will be remaining with only 4 instructions. That is 3, 4, 5 and 6. Now, as 2 bytes are remaining in the prefetched queue, it will get refilled. Why only after 2 bytes? Because 2 byte is equals to 16 bits. And as 8086 is a 16-bit microprocessor, it will do the operation on 16-bit, obviously. So after 2 bytes get empty, then only it will get refilled by next instructions. So here I made something to explain you how the instruction is refilled in the prefetched queue. Here we have a 6-byte of instruction already in the prefetched queue, and we have a 4-byte of instruction which is getting fetched for execution, and it will get obviously into the prefetched queue after the execution of these instructions. So assume this first byte got executed and now the queue got 1 empty byte. Will it get refilled now? No, it will not get refilled. Now this second byte will get executed. Now there are 2 bytes remaining in the prefetched queue. Now will it get refilled? Yes, it will get refilled. So these 2 bytes will get into the prefetched queue, and that's how it will get refilled. Now again, let's take this third byte. It will get executed and 1 byte got empty. Will it get refilled now? No. After the execution of the 4th byte, again 1 more byte will get empty in this prefetched queue. Now the remaining 2 bytes will get into this prefetched queue. So this is how the 6-byte prefetched queue gets refilled, only when there are 2 bytes empty in the prefetched queue. Now if someone asks you how many bytes of instruction are there in this queue, we don't know, because the instruction may be of 1 byte, 2 byte, 3 byte, 4 byte, 5 byte up till 6 byte. So the largest instruction is of 6 bytes. That's why we made this queue of 6 bytes, so that it can hold the largest instruction in this. Now you might have a question that how an instruction can be of different bytes, right? So see, I'll give you an example. Let's consider the assembly language that we write, that is move BL, CL. So this, I already told you in the previous video that this is a complete opcode. This will get decoded in the microprocessor. Now if I write move BL, 25H, then this entire thing is not an opcode, but only this part is an opcode and this is an integer or a number. So opcode can only be given to instructions or the register names. Opcode cannot be given to any number, because if I give the opcode to 25, then I can write another number also, that is 21. It may be 23, it may be 26, it may be 27. So I cannot give opcode to every number inside here. So the opcodes are only given to the operations and the register and the registers. So now here this is of 8 bytes, right? And if I write another instruction, that is move BX, 2000H, then This is again an opcode and this is again a number. And how much is the weight of this number? This is of 16 bytes. So this is how the instructions become of different sizes, and it will get into the prefetched queue based on its size. Sorry, this is bit not byte, and this is also bit not byte, because 25 when written in opcode we can write it as this, and this can be written as 4 and 1. So we have 8 bits, so that's why it is of 8 bit. And in the same manner, if we write the opcode of 2000, then we can write it 0010 and 0 for all this. So it will become of 16 bit. So that's the reason why instruction can be of many different bytes, and they are fetched into this 6 byte prefetch queue, and the maximum size is 6 bytes. That's why it is this prefetch queue is of 6 bytes. So as we saw, whatever instruction gets first into this prefetch queue, it will get executed first. So this operation is called FIFO. FIFO stands for first in, first out. So whatever instruction got first, it means, let's say 1 got first in this queue, so it will only get out of the queue at the first time, and after that, line by line, every instruction will get out of the prefetched queue. So the advantage of using this 8086 microprocessor is pipelining, because pipelining saves time. Now let's see why there is a disadvantage also in this pipelining, as the microprocessor expects that every instruction will get executed in a sequential manner. Let's take this first byte of this instruction is getting executed, and this instructions wants to call another line of instruction which is not there in the prefetched queue, but it is there outside of this prefetched queue. Let's say this line is getting executed and it wants to call this instruction, then the remaining bytes of instructions in the prefetched queue will make no sense. So these all instructions have to get discarded, or it should get out of this prefetched queue. So whenever there is a branch, this pipelining will fail. That means if any instruction is calling another line of instruction that is out of this prefetched queue, then all other instructions will get discarded, or it will get cleared. It doesn't mean that these line of instructions will get cleared from the code also. It will there in the code, but whenever there is a requirement, it can be called again. So that's why only momentary pipeline fails whenever there is a branch in this execution of the instructions. Now let's understand what this control unit doing here. See, these are the instructions in the prefetch queue. So whatever instructions are coming into this prefetch queue will first go into the control unit. So these instructions are understandable by us. It is understandable by human, but the processor cannot understand it. So these need to be converted into opcode. So when these are written, this control unit will understand it and it will convert it into opcode. Now if I write move BL, 25H, then this complete instruction is not going to get converted into opcode, but only this will get converted into opcode, and this integer will do whatever work is there with these registers. So move BL will get converted into opcode by the control unit, and the instruction will get understandable by all other things over here in the execution unit, and it will understand that what operation is going to be performed, and this integer will get into these registers. Whatever operation is required, it will get done. So we are done with bus unit interface. Now let's continue with execution unit. Here you can see that these are registers, and these registers are only used by us to do operations like addition, subtraction, or whatever another operations are there. So here this entire block is called as AX, and this is of 16 bits. But if I want to just use 8 bits, I can use it as AH and AL. AH means high, L means low. Now again in the same manner, we have BX, which is again of 16 bit, and I can use it as 2 separately, and which are of 8 bytes. So whenever I want to use 2-digit number, let's say 25H, then I can store it in AL or I can store it in BL. Now if I want to store 1234H, so that is of 16 bit. So I have to use AX because that is of 16 bit. So AX is having the capacity to store 16 bits of the data. So we will use AX to store that 1234H number. Here, as I said, AH stores higher byte and AL stores lower byte. Let's say I want to store 1234H in these registers. So 12 is the higher byte, so it will get stored in AH, and 34 is lower byte, so it will get stored in AL registers. And let's say I want to store this entire number in one register only, then I can store it in AX because it is of 16 bits. So 1234H will get stored into this AX register. So how can we write the assembly language for that? To store 12 in AH, we will write move AH, and to store the next byte, that is 34, we will write move AL, 34H, and Now to store the entire number into AX, we can write move AX, 1, 2, 3, 4, H. So this is the assembly language which is used to store this number in the registers. Now let's consider we want to add these both numbers, that is in AH and AL. So we can write it as add AH, AL. What it will do is it will take the AH value, that is 12, and AL value, that is 34, and it will get added. But where will it get stored? It will get stored in AH only. That means this operation is done as AH is equals to AH plus AL. Let's see how it is getting executed in the microprocessor. First, this add AH and AL gets into this control unit and it gets converted into the opcode, and this instruction says to release the AH and AL values which are there in AH and AL. So these two values, that is 34 and 12, will get released from the registers and will enter this ALU, that means arithmetic logic unit. So here it will get 12 and then here it will get 34, and these both two will combine and operation will get done and it will produce an output, that is 46. Now let's discuss something interesting. This is in AH and this is also in another register, that is AL. Now I can store this in AL, BL, CH or CL in all other registers except the AH. Again, now if I want to perform this same operation using AH only, will it get done? Let's see. If I write move AH, 12 will get stored in AH, and now if I say add AH, 34, then AH is 12 plus 34. So the operation will get done and the result will get stored in AH. So that's how we can perform the same operation using the same registers, and the other registers memory will not get used. So that's how the control unit explains to every part of this execution unit what operation should be done and what values should be taken from these registers. Now let's see what these registers are here. So these registers, as I explained you in the memory segmentation, that these are the offset registers. So CS offset register is IP, and again let me show you that figure. So here you can see that CS offset register is IP. So these are both in the same block, and now this stack segment registers, offset registers, are SP and BP. So these both are over here, and this data segment register, offset register is SI, so that is over here, and again the extra segment offset register is DI, so that is over here. And now let's discuss what are these operands and flags registers doing over here. Here the operand register and the flag registers. This operand register is temporary register which will store the temporary values whenever there is no space in these registers, and the flag register is nothing but it is used to check the status of the operation, that is done successfully or not, and that's the operation of a flag register, that's it. And there are few other registers also, but let's keep it simple. So let's see how this temporary register gets work, and let's consider we want to exchange BX, CX values, and if I put BX value in CX, then where should I put this CX value? Because if I put it somewhere else, it will get deleted or it may get lost. So that's why we use temporary registers where it will get stored, and after BX value is stored in CX, the value which is stored in temporary register, that is the value of CX, will get stored in BX. So that's how the temporary register works. So that's it for this video. I hope you have understood everything in this architecture, and if you did, let me know in the comment section, and don't forget to click that like button. Also subscribe to the channel for more such amazing videos, and thanks for watching.